Yeah.
Is enhanced beyond one test file.
Yeah.
Just what
Yeah.
What a similar thing has been seen in another spin chain system.
Okay.
Maybe I show the data already.
Okay. All right. So as I said, I mean, this is okay. Right. This. That's right.
But you are saying that despite the thermodynamics, you can explain further the impurities here or something like that.
Not often reported, there are not the system. Maybe.
So now we come to the story of cobalt. So when we dope cobalt, just 1% of cobalt in the system. So this is the pristine compound where the ordering happens at 5.5 K. With cobalt doping, the ordering temperature has enhanced to almost 10 Kelvin. And the system now behaves in a very anisotropic manner. So the susceptibility along the chain, parallel to the chain, and this is susceptibility perpendicular to the chain, and the transition is seen only when the field is applied parallel to the chain.
So this is the antiferromagnetic transition.
Yes, yes. So I want to point out that this is different from the zinc impurity where the transition was suppressed. Here the transition temperature has increased. Sorry, this is a repeat of the previous slide. Sorry. So now we put different concentrations of cobalt, and we see that the transition temperature scales with the concentration of cobalt, and this is the elastic neutron scattering peak for 1% of cobalt doped sample at different temperatures, and you see that the magnetic peak appears right below 11 K or so. So that's the proof that it's a bulk transition. And then this is probably the main slide of this talk. What we see in the case of cobalt is that let's first look at this panel. So here the field is applied parallel to the chain. B direction is the chain direction in this in 213 compound. So when we apply magnetic field, the transition temperature first decreases and then it's no more seen. And then with higher fields, a new phase transition appears, and this transition seems to become more robust and increases in temperature as the magnetic field increases. This has been seen in isothermal specific heat measurements also. So these are specific heat isotherms, and you see the one transition which is getting suppressed and then a new transition which is appearing. But this happens only along the chain direction when the field is applied parallel to the chain. When the field is applied perpendicular to the chain, it does what a typical antiferromagnet is expected to do, which means the transition decreases, transition temperature decreases slowly, gradually with the increasing magnetic field. So this is how the phase diagram looks like. So when the field is applied perpendicular to the chain, the Tn is gradually decreasing. When the field is applied parallel to the chain, this is what the behavior is like. So the transition temperature first decreases and goes below our measurement temperature limit, and then a new transition, phase transition appears, and in this phase the transition temperature increases. And this is for the pristine chain, both parallel to the chain and perpendicular to the chain, we see the same behavior. So there is a no, so this line is just for
why does the data end at 7 K?
Yeah, because you see this graph at above 30 kilohertz, the phase transition is not there.
So it just crashes?
Yes, it just crashes. So you see here we have done specific heat measurements under at 10 kilohertz interval. And the transition, this is the transition in the under the zero field, and then this is how it's diminishing and getting very broad, and now in the green curve we hardly see it, and then the new transition appears at the higher fields. There is, and this is confirmed also by the neutron. So this color plot, contour plot that you see is actually from the neutron data. So the neutron measurements were done up to this down to this temperature.
So it is what in neutron?
So it is probably the intensity of the magnetic reflection. I mean this peak which I showed you here.
So neutron seems to be catching the line, but bulk measurement do not. Is it a fair statement? Your red line that is drawn by hand.
Yeah.
That seems to be caught in neutron. Of course, I don't know whether the color scales have been adjusted accordingly, but it seems to be catching the neutron line.
That's right. That's right.
But the bulk signature disappears.
The bulk signature disappears. Yes, it gets very weak actually. It's difficult to see it.
That's why it's almost a vertical drop.
Yeah.
It's like because his heat capacity anomaly is very, very small.
Yeah. Can you give me 1 minute? Let me say this, and then the talk is done, and we can then discuss, because the time is almost done. So you see, this is now for 0.25% cobalt, and we see the same behavior, the transition disappearing and the new phase appearing. Then we try to all this data is unpublished so far. So we try to understand what's going on here, and we found that this actually is seen in another cobalt based system. This is an example of a Ising like chain. And here they have seen that at low temperatures there is a cascade of transitions as a function of magnetic field, and these are transitions from this longitudinal antiferromagnetic phase to longitudinal spin density wave to a transverse antiferromagnetic phase. And in the TAF phase, the transition temperature indeed increases with increasing magnetic field. Now what is interesting is that we can get this behavior, if indeed it is this behavior, by just putting 0.25% of cobalt impurities in this Heisenberg like chain. So we are getting the Ising like behavior. Now if we look at the
radium system is also chain system.
so here cobalt is spin half, vanadium is it's a Ising like chain. Yeah. So this is the phase diagram for XXZ model, and this is the Heisenberg point when epsilon is 1, and the ground state of this is Tomonaga-Luttinger spin liquid.
Just one. You are saying it's Ising because we are comparing it. Is there any other evidence for the
No. There is no evidence as yet. It's just the basis of this comparison. And now I want to extend this comparison a little bit further. So if you are in this domain, this is the purely Ising like chain, Ising chain, and this is the Ising like behavior, then something very curious happens. So actually above a certain critical field, the system goes from the Néel ordered state into a TLL state, but because of the presence of finite interchain coupling, this the TNN state is not stable because of the interchain coupling, and you are at low temperatures. Then you get this this longitudinal spin density wave transition, which is this region, and unless the field exceeds a second critical field, you don't get to this phase, which is the transverse antiferromagnetic phase. Now whatever I have understood so far is that in the TAF, these longitudinal correlations are weaker than the transverse correlation, which is always the case, and that is why in the pristine chain and in the zinc doped chain, the transition temperature was increasing with increasing magnetic field, whereas in this region, the longitudinal correlations are stronger than the transverse correlation, and that's why you get a phase sandwiched between these two, which is known as the longitudinal spin density wave phase. So if this is true, then low temperature measurements should reveal this. So I thought I'll cover this, but probably I will skip this part because it's already 2:30. The physics is the same in the zigzag chain, except that because they are zigzag, so there is an additional ferromagnetic interaction which brings in a certain degree of frustration, and that's why you see this ZFC-FC splitting and frequency dependence of AC chi. This is all known and very well investigated physics. So I will stop here, and this is the summary. We showed that dilute level of impurities can have significant effect on the ground state and excitations. So in the segmented chain we found gapping, and we see that the Tn is lowered, whereas with cobalt impurities we believe cobalt has on-site single ion on-site anisotropy, and which is getting induced to the entire chain, and that leads to this changeover crossover. I would like to thank my collaborators. So the crystal growth and bulk measurements are done at IISER by Kaushik, who is now in Dresden doing his postdoc. Rabindra is his junior, second PhD student. Neutron experiments were done by Marcos. He is a postdoc with Christian Rug, or he was a postdoc, now he has also moved. And Christian is the head of the neutron scattering group in PSI. And this work was actually done under this Indo-Swiss research grant, so my student could go to PSI and do the experiments. There were some USR data which I didn't show, and those were done by Giacomo Prondo, who was in IFW at that time and now is the editor of Nature Material. And these are the papers that we have published from this work. Thank you.
This phase diagram to show where this epsilon on the axis. Experimentally, how can you change the effect, incorporate the effect of epsilon by impurity concentration?
That's what I tried to show, that by doping this cobalt impurities, cobalt is known to have some, unlike copper, where the orbital angular momentum is fully quenched and therefore the spin is isotropic. In cobalt case, there's always cobalt salts are known to show highly anisotropic properties. So what we believe is that this anisotropy of the cobalt is getting induced in the whole chain, but it's very surprising that such small concentrations can change the behavior of the bulk.
If you change the cobalt concentration, impurity concentration, it is possible that you may see some other effect. Or
so as far as this phase diagram is concerned, I think we will probably see these fields changing. We have crystals with various cobalt concentrations, and we do see that the transition temperature in zero field scales with the cobalt concentration.
So you were saying?
Anyway, you have done a good job. I have two short questions. Just to complete the story, supposing they don't make any doping and they assume some defect, in other words, strontium 2, copper 1 - X, and then leave it as just a vacancy.
Yes.
And then perform and see whether there is any difference with the group samples and the pattern. Number 2, what happens if you disturb this strontium lattice by flashing?
That experiment has been done. So even with calcium doping at the strontium site, one see gapping in the spin excitation, but that happens for very high concentrations of calcium. More than, you need at least 10% of calcium to see the visible gap. So probably there you are going to the random singlet phase that I talked about in the middle of my talk, the theoretical work by Chandan Das Gupta and Eskema.
So you need off-stoichiometric copper site, what happens? My first question.
Sorry?
Off-stoichiometric.
Off-stoichiometric experiments have not been done. Those experiments are yet to be done.
Just prepare the space there. It's very, very okay. No, so you are saying that when that thing crashes down, it gets into an STW is because of the interchain coupling.
Because of the interchain.
Suppose you don't have an interchain coupling.
Then it will be
Then
a,
you go to the quantum liquid.
exactly, that's the very interesting thing. You go from nail ordered state to a quantum spin liquid state, which has a no classical analog.
So can you think about a system where that doesn't happen? Because that may be a cleaner way to look at it.
That's right.
This region. Okay. Fascinating. Thanks.
I think he had some question and I stopped him. Yeah, please.
I'll ask you one extension on Prof's first question actually.
Okay.
So you basically said a 3D7 or cobalt 3D7.
Yeah.
You expect to be in 3y2 state, right? So
Either
pieces are lower.
well, I probably should have that slide. Yeah, this one. So you see the 3D7 would mean you have to remove these two electrons. So you are left with one electron in the dxy orbital. So if the crystal field is very weak, then you might excite these electrons to higher levels and you might get high spin state of cobalt. But otherwise, high spin is, this is low spin.
The question is, I'm taking out 1% entity of copper and I'm just putting again 1%
Of cobalt.
So how it's making difference in properties of
Yeah, that's a good question. So copper 2 plus has a spin which is nearly isotropic because the orbital angular momentum is almost completely quenched, but that's not true for cobalt ions. I mean there are detailed theories for that were done maybe in 60s, and to be very frank, I don't understand those theories. Those are crystal field theories, but one can show rigorously that with cobalt one ends up with a strong on-site anisotropy.
but does it reflect in some view factor also?
Yes, of course it does. Yes. Of course. I mean it reflects in the bulk behavior. You see that the susceptibility shows a phase transition along when you apply field along the chain direction, but there is no phase transition when the field is applied perpendicular to the chain direction. So
And how do you assign the flavor to spin like Heisenberg to Ising?
sorry if the
So I'm saying you just said Heisenberg to Ising kind of transition.
right.
How do you basically
So I was trying to say that the pristine chains they are close to this point, the Heisenberg point, and when you dope cobalt you move towards this region, and your question is how one should explain this behavior. Of course it's very difficult to explain, and my hunch is that since cobalt is highly anisotropic, so the cobalt spin likes to point in a certain direction, and it makes copper spins, which copper spins are all coupled to each other, right, and they are coupled to cobalt, so that causes copper spins also to point in the same direction as the cobalt is pointing. Yeah.
Is it possible to define the experiments near the phase transition and we can define the Ising kind of Heisenberg kind?
That's a good question. Probably one should try those because these are very early experiments. As